Welcome everyone to the next session here on methods and methods development. In the beginning of this session, we've got a couple of speakers, and then we'll have a little mini break stroke overrun buffer, followed by three others before lunch break. So without further ado, let's get started. And the invited speaker in this session is Matthew Foulkes, and he's from Imperial College London, and telling us about solving the many-electron Schrodinger equation using deep neural networks. Matthew, over to you. The stage is yours.
Okay, thank you very much, Stuart. You can hear me and see everything okay?
That looks good to me.
Okay, right. So thank you for inviting me. This project started about a couple of years ago when three guys from DeepMind, David Foulkes, James Spencer, and Alex Matthews, approached me because I know about quantum Monte Carlo methods. And they were wondering whether using neural networks as a way of representing wave functions of many electron systems might be a good thing to do. So I worked together with them for a while, and we published a paper. And then just this year, I've been joined by two first-year PhD students. Gino joined me in October, and Halvard in January. Halvard is actually coming to England right now in an aeroplane from Norway for the first time, finally getting here. And so we've been working at Imperial College on this seriously for about a year, but with the DeepMind guys about 2 years. So let's start with an introduction. We in materials physics and quantum chemistry are lucky in a sense because we already know a grand unified theory. It's the Schrodinger equation for many electrons. I think most of us listening to this talk are probably confident that if we could actually solve it, we would learn most of what we want to know about materials, for example, or about chemistry, just by solving this equation. Here's the Hamiltonian we need to deal with. It's just to set up notation. Ri are electron coordinates, and D subscript capital I or J are ion coordinates. Z are atomic numbers. So we all know that this would be a nice thing to do, but of course it's a very hard equation to solve. In fact, there are papers showing that at least in certain examples, it's NP hard, the many fermion problem. And that suggests to me that the best we can realistically hope for are approximate results. The other problem is you need to solve it really accurately. At room temperature, KT is about 25 milli-electron volts. So if you wanted, for example, to do room temperature chemistry, you need an accuracy on that scale or better. Chemists actually are a bit milder than that. They talk about chemical accuracy, which is 1 kcal per mole or 43 millivolts per particle. We're going to work in millihartrees mostly here, so it's 1.6 millihartrees. But whatever it is, it's unfortunately several orders of magnitude below the natural energy scale of the Schrodinger equation, which is the hartree. You know, even a single atom can have a total energy of hundreds or thousands of hartrees if it's a many-electron one. So in a way, solving the Schrodinger equation to find out about chemistry is a bit of a fool's errand. It would be better if we had a lower energy effective theory that allowed us to do this without this wide range of numbers in our calculations. But unfortunately, we don't really. I don't know of anything that gets chemistry right that's really much simpler than solving the Schrodinger equation. So how can we solve it? The most widely used method by far, and for good reasons, is density functional theory. It's a kind of nice balance between ease of calculation and reasonable accuracy. It can sometimes even get chemical accuracy if you pick the right exchange correlation functional, but you can't really tell what's the right one in advance. And it misses quite a lot of information, of interesting things. For example, it's not really going to be able to tell you about different quantum states, different quantum phases. You know, it's not going to tell you that the system's going to go into a fractional quantum Hall state, because that kind of thing's not going to have been built into your functional. In principle, it can, of course, but in practice, it seems very unlikely. You can do perturbation theory, like we just heard Lucia Reining talking about beta salpeter and GW. Those methods work really well, especially for weakly correlated materials. But again, it's not clear what you will do if you have a really strongly correlated system or a non-Fermi liquid ground state. There are some other approaches we could talk about, but I'm not going to, like DMFT. That's also useful in its regime. But one of the methods that's actually most widely successful in quantum many-body physics has been just guessing the wave function. let's go back through a bit of history. The BCS wave function, Bardeen, Cooper, and Schrieffer explained superconductivity, conventional superconductivity, just literally by guessing the wave function. There's a phase transition between the superconducting state and the Fermi liquid state, so you can't easily get there by perturbation theory. Bob Laughlin explained the fractional quantum Hall effect by some kind of utter brilliant guessing of the wave function. I don't know how anyone could have done that, but he did. The beta ansatz solves many 1D problems. So it's kind of indirectly responsible for ideas like spin charge separation. So there are lots of these things. If you want to find out about states you don't already know, this seems to be as good a way as any. And there's also a big industry of what you might call parametrized wave function guessing. Hartree-Fock is the simplest, where you just say the wave function is a determinant, and I'm just going to adjust the one particle orbitals. That's the guessing part to make the best determinant I can. CI says I'll choose a basis set and I'll expand the wave function as a linear combination of determinants made from functions in that one electron basis set. If the basis is infinite, of course, that's solving the Schrodinger equation properly, but for a finite basis, it's a sort of parametrized wave function guessing. I'll talk a bit about Slater-Jastrow, but coupled cluster is widely used in quantum chemistry and getting useful in solids now. That's also a kind of trial wave function. So a lot of these things are wave function guessing. It doesn't seem like a very good approach, but it is quite a useful one if you want accuracy beyond DFT. And Ferminet, the thing I'm going to be talking about today, nicely named by David, not by me, is just another kind of guessed wave function, really. It's represented as a neural network, but it's just a guessed wave function. So I'll just remind you, if you don't already know, about how variational quantum Monte Carlo methods work. You start by guessing a wave function. T stands for trial here. You evaluate the energy expectation value by doing this 3n-dimensional integral if you have n electrons. I'm not writing spin in these equations, but of course there are spin coordinates as well, really. And the way we do that integral is with Monte Carlo integration. You multiply and divide by psi. So this psi star goes along with one of the psi's to make a mod psi squared. And then we have h psi over psi here. And so this whole part here, the mod psi squared, is a probability density in this 3n-dimensional space. And so you can sample points in the 3n-dimensional space from that probability density using the standard Metropolis algorithm. And then this is your score function. We call that the local energy. And so essentially you throw darts into your 3n-dimensional space according to this probability density, and you average the scores of those darts, and that gives you the expectation value of the energy. And then you just adjust all the parameters in your trial wave function to make the energy as small as possible, and you say that's the best I can do within this functional form. I've chosen a functional form for the trial function, and I'm restricted by that. The simplest form that's often used, and is surprisingly actually quite successful, despite its simplicity, this is for large systems, for solids. You just take a single determinant, usually made of DFT or Hartree-Fock orbitals, and you multiply it by something that suppresses the value of the wave function when any pair of electrons gets close together. The idea is that that helps the electrons stay apart, makes it less likely to find them too close together. Because in the determinant, although exchange is there and spin parallel electrons can't get on top of each other, spin anti-parallel electrons can, and that costs energy. So this builds in correlation in a very simple-minded way. And you have some parameters in the determinant, and this is called a Jastrow factor, and you optimize them. The nice thing about this is it works okay in weakly correlated Fermi liquids. You can study systems of thousands of electrons, and it's incredibly simple. You can code it in about half an hour, except for all the fiddling around with wave functions anyway. That gets complicated. Limitations, it's not, this kind of simple trial wave function I just talked about is not anywhere near capable of chemical accuracy. In fact, it's not really much better than DFT. It just has different weaknesses from DFT. Of course, you can use it as the starting point for then a more accurate calculation, a projector method like diffusion Monte Carlo or auxiliary field Monte Carlo, and they get much better. They do get to chemical accuracy just about. And then the other question is, how do you extend this trial function when it doesn't work? You could say, I'll do a linear combination of determinants, but that doesn't scale well. And it's no help when the Fermi liquid physics is very wrong either. You're starting from the wrong place. So now we get on to what we did. The first observation that I think David Foulkes had really is that well, we all knew this, artificial neural networks are flexible and efficient function approximators. There's a huge amount of hype about them, but that's all they are. They're function approximators. You put in some numbers at the input and some numbers come at the output. It's just a function. And you're just using the network to represent a function. So perhaps we can represent the wave function as a neural network. And they're also very good at high-dimensional functions, because the biggest problem about this is even if we have just, say, 30 electrons, this is a 90-dimensional function plus the spin binary variables. And but neural networks can do that, because an image of a cat with 1,000 by 1,000 pixels has a million numbers in it, maybe times 3 for red, green, and blue. And they can represent functions of images of cats onto, is it a cat or not? So yes, it might be able to do that. And for those of you who don't know about neural networks, neither do I. I'm not a neural network guy at all. So this is my baby view of what a neural network does. It's really just a computer program. It is sometimes implemented in specific special case hardware, but it's usually just run on GPUs. Actually, that's what we're doing. And so but it was originally modeled on the brain. And so it has things inside it that you can call neurons, which are really just places numbers are stored, honestly. So here's a neural network where you put in 4 numbers. They go into this initial layer of 4 neurons. The data from each of these neurons is passed along the arrows to the next layer. There may be multiple of these so-called hidden layers. And what these arrows actually represent is a linear transformation. So the value at this neuron is a linear combination of the value at the 4 below. So this would be a 5 by 4 matrix here, acting on the 4 inputs to get the 5 hidden layer values. And that's the matrix W here. You can also add biases, which are just adding a constant vector. So that gives you a mapping from this layer to this layer, but so far it's just linear. And even if we have multiple layers, a composition of linear transformations is still linear. So you don't gain, it can only represent linear functions at the moment. The trick is that once you've got a value at this hidden layer, by doing the matrix arithmetic here, you pass it through a nonlinear function, that value, which it's modeled on the brain. So if the input is small, it gives 0, and then it rises. And if the input is large, it gives 1, essentially. We use a tanh function. And then we go through multiple layers like this, and out comes an output. The reason neural networks became so popular in the last 10 years is that there are extremely efficient algorithms for updating all the parameters, all the matrix weights here and biases inside. They use what's called automatic differentiation and backpropagation. They're technical, but they are very, very clever indeed and very efficient. And it was realized really by big companies initially that if you run this kind of thing on large enough hardware, it can do a surprisingly good job at approximating functions. So that's all very good, but we don't know the function we want to approximate. We don't know the wave function. And we don't want to try and learn it from data because we don't have enough accurate wave functions to use as data. So instead, we learn it by variational Monte Carlo. We learn it from the variational principle. So our network has 4 inputs, this one, 4 electron positions. Maybe you could call that 12 inputs, a bunch of layers, and then one output, which is the value of the wave function. We have not very many layers, typically 4, but the layers are quite wide. They have hundreds of nodes in them, hundreds of neurons in them. So we choose an initial Psi-trial squared, which is actually random initially, within some limits I'll explain in a minute. We sample points from it using the Metropolis algorithm. We estimate the energy expectation value. Neural networks will give you the first derivatives as well. And then we just adjust the network parameters to lower the variational energy. So it's absolutely standard variational Monte Carlo. The second observation was we tried to come up with a wave function that would do more than Slater-Jastrow, but was easily represented in a neural network. And one of the things we noticed, sort of backwards actually, by fiddling around rather than by great insight, was that if you take the orbitals in a Slater determinant, they don't have to be functions of the coordinates of a single electron. We can generalize the idea of a Slater determinant. The only requirement, of course, is that if you exchange, say, R1 and R2, you flip, in this case, the first 2 columns of the determinant, so the sign changes. So you can do more than just a single particle orbital in the determinant. You can have a function that depends, yes, on the position of one of the electrons, but also on the set of positions of all the others. So I write that as the set of R not J. as long as the dependence on the elements of this set is independent of the order of those elements, so it's an unordered set, it's easy to convince yourself with 10 minutes fiddling around on a piece of paper with an example that this determinant is still antisymmetric. And so what FermiNet, this neural network we've built, actually does is represents, optimizes, and evaluates sets of permutation of these functions, these generalized one-electron orbitals. Okay, so our determinant, we usually have just a few determinants up to about 16, and they don't contain Slater one-electron orbitals. They contain these things, and FermiNet generates us enough of these things to fill up our determinants. We start from random, and we put no chemistry in. We don't say, oh, this is a p orbital, this is a d orbital, or anything like that. We don't even put in, restrict kind of configuration interaction ideas about which orbitals are full and which are empty. We just let the network do its thing. This is not an entirely new idea. The idea of generalizing one-electron orbitals goes back to the idea of backflow by Feynman and Cohen, and was first done in a neural network context in lattice systems by Luo and Clark. We're going further than either of those did in the form we're using here, considerably further. There's also some interesting work by Holtzman and Moroni and people about what's called iterated backflow, which does something similar. So it's not entirely new, but it was the first time this had been done in a real molecule. So let's look at some results now for the rest of the talk. So far, we've really only, or at least the only results I'm going to talk about are on molecules. We are now beginning to do electron gases and solids. I'll talk briefly about that at the end if there's time. But I'm not really ready to present those results yet. It seems to be working is all I'm going to say. So here are some atoms. These are the first two rows of the periodic table. And we just solved the ground state energy of an atom using FermiNet. In all cases, we used exactly the same FermiNet. In fact, for all the results I'll show you, we used exactly the same FermiNet. So it's always got 16 of these general determinants in it, just 16. And the other calculations here are done using a bunch of really quite good methods, chosen because they're methods that may be usable in larger systems. Most of the really accurate quantum chemical methods like CI can't scale at all. These ones all scale reasonably well to larger systems, at least sort of 50 electrons or so. We did those calculations well, or we took them from the literature. This VMC and DMC, for example, was done by Richard Need's group in Cambridge, and they did a really good job with literally many thousands of determinants in their trial functions. So it was a really much more difficult thing than what we did, really. Couple cluster is singles and doubles and with perturbative triples is what quantum chemists call their gold standard for large systems anyway. And you can see that FermiNet, which is the green one, is pretty much as good as any of them, and is attaining chemical accuracy. This gray bar is chemical accuracy. This was, within a few months of beginning to even think about this. We can add and remove electrons. These are ionization potentials and electron affinities, and these are actually errors relative to experiment. They're all negative, which is kind of interesting, I think. I'm not sure why. But they may look like big bars, big error bars here, but 1.6 millihartrees is one chemical accuracy. So they're all within chemical accuracy. So we can do adding and removing electrons. One of the things that's interesting about our network is that many electron wave functions have cusps in them. For example, if one electron here, this one, approaches a nucleus of a helium atom, there's a cusp when it passes the helium nucleus. Just like in a hydrogen atom, e to the minus r over a naught would be for a hydrogen atom. There's also a much smaller cusp here when this electron passes the other electron. I put them in a line in this example. We don't put those cusps into our network, and our network is entirely analytic. Everything in it is smooth. We really want that to be the case, because otherwise Monte Carlo methods have trouble, because you miss delta functions for example, if the Laplacian has a delta function in it, you won't sample that properly and you'll get the wrong answer. So how do we get sharp behavior? This is results from our network when we didn't put it in. The trick is that among the input variables, we put the absolute value of Ri minus Rj for all pairs of particles. And that absolute value function, even before you enter the network, has a cusp in it when the two particles are on top of each other. So that allows the network to learn the cusps, and it does a fantastic job about this. There's exact results here for these cusps, and this should say -2, and this should say 0.5 for an electron-electron cusp, and it's very close. Because we've got a many-electron wave function, we've got access to many variables you can't see in, say, DFT. These are exchange correlation holes, just to show you we can do it. We've done a bunch of molecules. So here are a bunch of molecules, starting from lithium hydride and going up to bicyclobutane. This one has 30 electrons, all done with exactly the same network we used for the atoms. And you can see that as the system is getting bigger, the errors are increasing. This little bar is chemical accuracy. But if you divide the error by the number of atoms or the number of electrons, even better, you find that the relative error is not increasing very fast at all. There's no sign it's exponential at the moment, I would say. So we don't really know how this will scale when we go to much bigger systems, but it's not looking bad. And again, it's better than all these coupled cluster methods, done really well. I must admit that if you do coupled cluster and then you do what's called an extrapolation to the complete basis set limit, coupled cluster is often lower in energy than us, but we are strictly variational, and coupled cluster, of course, isn't. So I think we don't quite attain coupled cluster accuracy in most of these molecules, but we're incredibly close. And we do beat coupled cluster without a basis set correction. I just wanted to show that we're getting, forget all the numbers in this table, we're getting 99-point-something% of the correlation energy in all these molecules, except for some reason bicyclobutane we found hard. We don't really understand why. A typical variational Monte Carlo calculation might get 85%. So we're a couple of orders of magnitude better. The other thing I wanted to show you is that quantum chemistry is really hard. This is the energy of a molecule here. 99.5% of that, more or less, will be described in a mean field method like Hartree-Fock or DFT. The green bit here is the correlation energy, which I zoomed in on here. And the red bit here is the error we're at. And we're only just good enough to do quantum chemistry at room temperature. So it's a really tough problem. I made that point at the beginning. Solid state physics is much easier because there are very few methods that will extend to doing solids, and the expected precision is much lower there. We can pull molecules apart and look at how the energy depends on spacing and watch bonds break. And we can cope with bond breaking quite well. This is a coarse view. The bottom one is a zoomed in view of the top, and the bottom one shows the error relative to experiment in the energy of the nitrogen dimer as a function of spacing. Our yellowy ones here are Fermi-net. The blue ones are a good coupled cluster calculation. This is some fancy quantum chemical method. I don't even really know what it is, but we're as good as anything again. We also did a bigger system. We've currently only really gone up to about 50 electrons, and we are finding it hard to get larger, but this is not 50 electrons, this is just 10, but it's got 10 atoms in. This is not a real molecule, of course, 10 hydrogen atoms in a row, but we looked at it because there was a nice paper a couple of years ago in PRX where a selection of groups from all over the world got together and they all decided to study this particular molecule as accurately as they could. And they applied all the best methods they know, and we've reproduced from their paper all the most successful ones here. And this is again a zoom in. We don't know the exact energy, but this green shaded region is where the authors of the paper thought the exact energy was. And again, all we did is we added our variational Monte Carlo result. And it's as good as anything again. To me, this is very exciting because variational Monte Carlo is a lovely method. It's incredibly simple. You can measure anything you want. You can get all kinds of data out very easily. We can do a slightly more interesting chemical reaction here where we turned bicyclobutane into butadiene. I'm no chemist, by the way, so I don't really know whether this is interesting. It's just one we chose to do because other people had looked at it. And you calculate the energies of all the intermediates relative to the starting state. Fermi-net's down here. DMC has been done by other people very well, we think, and agrees with us very well for all of these energies. And it's quite a different method. So we're using a very different trial function. And we do better, actually, than the coupled cluster methods on these relative energies differences here. The experimental result for this ConTS molecule is very similar to ours. This one is quite different from both our results and all of the others as well. So we're not really sure what's going on there. Something is different about butadiene Maybe we've got the geometry slightly wrong. Maybe the experiment is slightly wrong. We don't know. More recently, we've been looking at positron affinities. So far, I've just reported results of things that other people can do, which is fine, but not very exciting. Positronic molecules are quite popular in chemistry at the moment because people can make them and measure the affinity of positrons, and because the presence of the positron, which eventually annihilates but stays around long enough to allow you to measure it, the presence of the positron can change the chemistry, and the molecules can change shape when the positron arrives and things. And it's quite hard to calculate these things using conventional quantum chemical methods because people don't really know where the positron's going to go and how diffuse it is, especially in non-polar molecules. And so they have trouble with basis sets, basically. So for this one, lithium hydride, we did this, the grad student who was doing this, Gino, wrote the positron into the Fermi net in one night, well, maybe one day and a night, and then started getting results the next day and was within really accurate values of these are accurate calculations. For these small molecules, there are accurate methods available, and we essentially reproduce them perfectly. We do slightly better than the fusion Monte Carlo in this particular molecule. You can see the positron hangs around outside, avoiding the nuclei. This is a beryllium oxide one. The interesting thing here is that this was our result. The DMC result was a factor of 2 out. And our result is better because both methods are variational and we're getting lower energies. So the DMC was somehow having trouble with this molecule. There's a quantum chemistry result which kind of agrees with us. The reason this is interesting is because we can go and look at positrons in much larger molecules beyond the scale of where these very complicated quantum chemistry methods work. At least we think we can. We've also done a little bit, maybe I'll skip this. We've done a little bit of diffusion Monte Carlo using Fermi net wave functions as the basis, as a starting point. So, diffusion Monte Carlo will improve any trial wave function you give it to some extent. The sad story, which I won't bother with the numbers, is that the improvements we got by running diffusion Monte Carlo on top of our variational wave function were very small. That's telling us that there isn't much more to be gained by doing diffusion Monte Carlo. I was a bit disappointed by that. So to try and finish on time, here's an outlook. Ferminet is way better than any other kind of variational Monte Carlo that's previously been applied to real molecules with more than a couple of atoms. It's the accuracy we get, despite the simplicity of our approach, rivals coupled cluster for equilibrium geometries, and sometimes does better for strongly multi-determinantal molecules and bond breaking and things like that, which are of course important in chemistry. It can serve as a trial function for diffusion Monte Carlo and other projector methods, although we were disappointed with what we gained when we did that. One other person has tried that too. We've only just begun, and we're fighting methods that have a 50-year head start. Where I think we're going to be most useful is looking at systems where we have very little idea of the wave function. So I wanted to go ahead and tell you some previews of what we're doing now. This will take just 1 minute. Sorry, Stuart. We've been looking at electron gases, and for example, when we made the electron gas density lower, the Fermi net spontaneously found a Wigner crystal emerging. We can't do very large systems at the moment. These were only 30 electron gases, so the absolute numbers won't be right. Probably there'll be size effects, but it's telling us that we can do quantum phase transitions without knowing them in advance. We didn't tell it had to be a Wigner crystal. It just came out that way. We've also implemented pseudo potentials to allow us to do heavier atoms without so much computational cost. They do cost still quite a lot, but at least we've done it, and we're beginning to look at little boxes of real solid now, because I'm a solid state physicist, not a chemist. The questions are, how general is our trial wave function? Should it in principle be able to get the right answer? We have a piece of maths that says yes. In practice, no, not at the moment. We can't do it certainly not with one of them. Can we really get away with only 16? That's all we've ever tried so far, and we've always got away with it so far. But maybe the number you actually need rises exponentially with system size, in which case we're back in the CI problem. What's limiting our accuracy? We don't really know. Is our wave function, our approach, size consistent and extensive, and size extensive? Quantum chemists care about these things, and solid state physicists should certainly care that we get an extensive energy as we make the system bigger. How can we do larger systems, bigger boxes of solid and larger molecules? I must admit we can, in principle, there's nothing stopping us, but it's taking us, we're finding it painful. It takes a lot of computer time and a lot of memory, and we're now running on the new kind of Ampere GPUs with lots of memory, so that memory is not holding us back anymore, but the cost is still quite high. And pseudo potentials and solids, as I said, we've already started on. So that's all oh yeah, we're not the only people doing this. It's very fashionable, like anything with neural networks. And if you want me, I better stop now, but I'm happy to explain some of this if there are questions. Thank you very much.
Okay. Thank you for that. Well, you've used your question time, but let's just do one very quick question, because you feel as if we must do questions, don't we? Yeah. So let me just do sort of the first one that appeared during your talk. There's this one here, which is a very nice talk. I completely agree. I was wondering what the absolute reference is for your benchmarks, atoms, molecules, experiment, or something like FCI.
The absolute reference, where we can, we use experiment, but you have to then take away vibrational effects and things. Most of our references for very small molecules were either done, well, actually, when I put a 0 in, that was either experiment or some very accurate CI-like calculation. For larger molecules, we don't have, in many cases, better references, so we're really mostly comparing ourselves against coupled cluster, which is and coupled cluster with basis set extrapolation as well. I'm not sure if I answered the question right, but that's my best one, best attempt.
Thank you. I see there's a couple other questions, but unfortunately we must.
Yeah, I'm sorry, I went on a bit long.
That's okay. Maybe you can chat to folks in the booths later on during lunch or something.
Yeah, I will. Yeah, I'll be there. I have a meeting at 1 and 2, but I'll be there until then.
Right. So, let me just tweak this around, and if I do that, I think we're there. Max, if you can start sharing. Our next speaker this morning is Max Nusspickel. I've probably mispronounced your surname there. Sorry about that.
That's right.
He's from King's, and he'll be talking about systematically improvable quantum embedding for real materials. Max, the stage is yours.
Yeah, thank you. So we're going to stay with wave functions for a little bit, and I would like to start with a quote by David Foulkes, who said that the wave function of a many-body system is so complicated that any approximation to it will be almost orthogonal to it. And then Walter Cohen, one of the inventors of density functional theory, went even further and said a wave function of 1,000 or so electrons is not even a legitimate scientific concept. And we can see the effects of that. So apparently the many-body wave function is a very complicated object, and we can see the effects if we think about how solid materials are modeled today, in that we mostly use properties such as, or quantities such as the electron density, density matrix, or Green's function, electron propagators, to describe a quantum system. And very rarely do we actually use many-body wave function. Seems to contradict maybe a little bit the introduction that Matthew just gave in his very nice talk. But I would still argue that the bulk of solid-state modeling is really density functional theory or some of these methods. Now, this is a bit of a shame that we can't really use many-body wave function because they have very nice properties and advantages. For example, they can very systematically include electron correlation. And this is something that density functional theory obviously struggles with quite a lot. There are no problems with any kind of representability. So questions like, does this Green's function correspond to a physical fermionic wave function or not, do not have to be answered if we work with wave functions from the beginning, which have the correct symmetry. And maybe in response to these two quotes that I started with, I would say that you shouldn't measure the quality of a wave function by the overlap with the exact wave function, but rather by the properties you can calculate from it. And it turns out that bad wave function can quite often give you still good energies, for example, which is something that for example, electron density you can't do. If you have a bad electron density, you have a bad energy, except if it's maybe accidentally correct, but that's not really what I mean here. It's more systematic, really. So fortunately, there is somewhat of a saving grace if we want to use wave functions in our field, and that is the principle of locality, because it turns out that for the low energy Hamiltonians of electronic structure theory that we're interested in, this complexity of the wave function is a bit of an illusion. And nature doesn't really explore this really large Hilbert space, but the kind of physical kind of low energy states that we're interested in usually have fairly low entanglement or are local. Basically, if you perturb the system somewhere, you won't really see the effect in a distance of 20 angstrom or so. And this locality can be used to derive methods. And so I've done this work with George Booth, and we developed a new quantum embedding methods for real solids. There's a preprint available online. And this has locality built in from the start. It is systematically improvable to a canonical coupled cluster result, while at the same time it retains a hybrid DFT-like scaling. And as it's systematically improvable to coupled cluster, it's kind of doesn't have any empirical parameters opposed to something like hybrid DFT. So I already heard Matthew talk a bit about coupled cluster, but I just want to motivate a bit more why we think this would be a nice method to use for solids. First, it's proven to work very well for molecules. Quantum chemists use it all the time. It's a diagrammatic theory, and it contains many diagrams of something like GW, which would be considered a very good theory for solids usually, and then some more. So its diagrammatic content is quite good. It's not actually a subset of a GW diagrams. There's some in GW that are not in coupled cluster, but it also has many more. And it has infinite resummations of diagrams, so it can really describe, it can be applied to metals, and it contains diffusion. So it's something that we really would like to be able to use for solids. But and there are implementations, but it's just computationally too expensive to really use it for anything but real trivial systems. But here, for the first time, we think we kind of are able to apply to something that kind of mimics a real material, really. So I'd like to then outline how we do this. And first, this is really an outline that you could think of any quantum embedding strategy with these 4 points. So the first step is you divide your system into some sort of fragments. And then the second step is that for each fragment, you want to derive some kind of description of your environment. And this is usually called bath. In the quantum embedding community, or even though you shouldn't think of any thermal bath here. And then the third step is that you, for each of these combined fragment and bath spaces, which we also call cluster, you use your method of choice to solve it, so coupled cluster in this case. And then the fourth step is how can we deduce expectation values from these various cluster calculations. So let's go through these steps and see how we do this. So in step 1, we just choose atomic fragments. So we simply focus on a single atom. And I've shown this here at the example of a carbon atom in a 2D material, graphene, where we just span the fragment space by its atomic orbitals, 1s, 2s, and 2px, y, z. So this confirms the claim that the locality is built from the beginning. We start with a local fragment. So let's move on to step 2. And actually, this is step 2a, because it turns out that we need, or we use in our method, we use 2 types of bath orbitals. So the first type is known from a quantum embedding theory called density matrix embedding theory, or DMET. And I again visualized them here for this particular graphene system. And you can see they're mostly localized on the direct neighbors of the carbon that we want to focus on at the moment. And another important property about them is there's only as many as you start with fragment orbitals. In this case, we get 5 DMET bath orbitals back. So what they do in principle is they make it possible to factorize your mean field wave function between this cluster part down here and an unentangled environment part like this. Because of course, in general, if we start from a fragment, you can't really, the general wave function won't decompose in this way because it has some kind of entanglement. But the DMT bath orbitals are exactly the bath orbitals you need to add in order to make this decomposition on the mean field level possible. But I think it's clear that these few bath orbitals can't really describe the true environment, and they can't capture all the kind of correlation effect, all the excitations into the larger lattice. So clearly we need to go beyond this if we want to get accurate results. And this is where we introduce a second expansion of the environment. And here we actually use a correlated level of theory, perturbation theory, a Muller-Placid perturbation theory. And we use the first order correction to the environment density matrix. We construct this for each of these fragments. And then you can just diagonalize this density matrix, and you get some eigenvalues. And these eigenvalues give you kind of a natural ordering that tells you about the importance that these orbitals have in the description of your fragment that you want to calculate at the moment. Basically, large eigenvalues means these orbitals are important, and small eigenvalues mean they are less important. And then all you have to do is to define a threshold, which we call eta in this case, and you keep all the eigenvectors corresponding to eigenvalues larger than eta. You keep those as bath orbitals, and the rest you keep frozen on the mean field level. And this I've visualized down here for 3 different values of eta, and you can see as we lower the value of eta, you increase the size of this final space that is active in the calculation, and you start to explore more and more the environment of the single atom that we kind of want to calculate. This idea, I should say, is very much related to something called pair natural orbitals that are frequently used in local quantum chemistry. It's a bit of an extension to it because we use it to both generate occupied and virtual orbitals in the environment, whereas in quantum, these PNOs are usually just used to create virtuals. And they are also not just for a pair of occupied orbitals, but we kind of generalize them to a whole kind of atomic cluster. So that's step 2. Then, an important question actually is, how does this red blob that I just showed, how does that change if we increase the system size? So this is an important question to answer. And here I show for diamond, I show different supercell sizes from 111 to 666, and the number of active orbitals that you end up with in your cluster on the y-axis. And I do this for 5 different values of eta. And what you can see is that initially you see an increase in all of these curves, but then they settle to a plateau at around 333, 444. It becomes a plateau. And this is quite important. It means that we can grow our system further, but the cost of our correlated calculation doesn't actually, of the solver part itself, doesn't actually increase. There's some, of course, some costs associated with preparing integrals in the cluster and so on that still scale, but they're actually not the bottlenecking step. They're all 3rd order with system size. Now, our bottleneck really in this method is the mean field that we have to do in the beginning, the Hartree-Fock calculation. And this is a situation that is completely analogous to hybrid DFT, where also your bottleneck is the evaluation of exact Hartree-Fock-like exchange. So we kind of have the same computational scaling, we argue. Step 3 and 4 are fairly straightforward. Step 3, just we project into the active space that we kind of that I just talked about, and then we have to consider that there's some core electrons which are frozen, which contribute still a Coulombic exchange potential. But then we can just solve this cluster Hamiltonian with coupled cluster. 4 is a bit more interesting because we do something fairly non-standard here as well, which is not usually done in quantum embedding theories as far as I'm aware, is that we actually define a global wave function. And how this is done is that each cluster wave function in coupled clusters is expressed in terms of these T amplitudes. And they have either 2 or 4 indices. And then we say, okay, how can we deduce from these cluster amplitudes, how can we deduce something which we would like to think of as a global wave function? We just project one of these indices, and we just choose the first occupied indices, on the fragment space of the cluster X that we're currently considering. And then we can simply sum up all these contributions of all clusters, and then we have something that we consider the global wave function. And from that, you can then easily calculate the total energy. using normal equations. But this really tells you how to calculate any expectation values. I should say this is not really how we do it in practice, because you don't actually want to allocate such a large object over your entire system, but you can kind of contract energy contributions as you look over the clusters. So it's something that can also be done efficiently. Now let's finally look at some results. And this is diamond again, a 555 supercell. This is 250 atoms, triple zeta base set, which is 7,500 orbitals. If you know couple cluster, you know that this is kind of out of the reach of canonical couple cluster solvers. But here we just vary the lattice constant and plot the total energy for 4 different values of eta. And the eta gets lower as we move down. So the most accurate result is the green curve here. And the first thing I want to really stress is that except for the blue line, these curves are very smooth. So we fit them with an equation of states, and all the points lie precisely on it. The fit is very well conditioned. For the blue line, you can see a little bit of an outliner here, because this is the least accurate calculation. So why do I stress this? Basically, what you have to consider is that these different points have completely different bar spaces, right? Even the number might change. You might get 200 sparse orbitals here and 190 here. So it's quite easy to get kind of discontinuous curves. But here the precision is really so good that we can fit an equation of states quite nicely. We can determine the minimum, which tells you the equilibrium lattice constant. And it's an excellent agreement with experiment, which is the gray dotted line. And we can also compare this to other methods that are out there, DFT, and we are in better agreement with experiment, and also in better agreement than a canonical couple cluster calculation that's been done on 54 atoms. Finally, here again, I show the in blue the lattice constant as a function of your cluster size and converges nicely, and also the bulk modulus in red. It's a bit overestimated compared by the experiment. But keep in mind, this axis also doesn't start at 0. This is about 3% overestimated here, so it's not terrible. You might ask, can we do something more interesting, something like a metal? So here we look at graphene, which is a semi-metallic 2D system, and you might think this can't work very well because the perturbation theory, MP2, that we use to construct Barth orbitals isn't really supposed to work well for gapless systems. But in the end, we still use a couple cluster method to solve our clusters, and it seems that this is good enough. And we get, again, for the lattice constant, we get excellent agreement with the experimental range and a scatter of DFT results as well. But I think where this method is really the strongest is if we think about systems which have a bit more strong electron correlation, because this is where DFT really starts to struggle. For example, for partially filled 3D or any D or F shells, you get some strong correlation, and DFT often has problems with this. What you can do is you can start to look at an ad hoc approach such as LDA plus U, where you add a little bit of Hubbard U-like potential to your 3D states. But then the question is, what U should you use? And now with our embedded couple cluster method, we kind of for the first time can really give an ab initio high-level reference that you can look at. So for example, here I plot for different methods the number of electrons you find in either the T2G or in the EG set of orbitals. And the dotted line is our coupled cluster results that we produced. And then you can, for the LDA, you see Hartree-Fock underestimates it, LDA overestimates it. This is often a situation you find Hartree-Fock is on one side, LDA is on the opposite side, and the truth is somewhere in between. Here you see LDA plus U results for different values of U. This is the value that's most often used in the literature. And you can see this gets at least the splitting much better than without using a U, but they're still slightly overestimating. And there isn't really a value of U where you kind of match our CCSD results, but that's to a certain degree that's expected because this is kind of still a crude method. But yeah, now we have a possibility to really validate these results. Now with this, I'd like to come to my conclusion. First off, where are we going to go from here? At the moment, we are implementing this in a spin unrestricted form, such that we can look at at magnetism. So that's fairly straightforward. We'd like to look more at strongly correlated systems. As I said, I think this is where the strength lies, and look at different properties as well. Then ultimately, if we want to do hybrid DFT or want to compete to hybrid DFT, we'd also need to address how we can actually derive a spectral function from this. And it's not quite clear yet how we're going to do this, but this is something we want to attempt as well. If you want to see details, there's the preprint available online. And with that, I'd like to thank for your attention.
Thank you, Matt. If we have any questions, can you take them into the Q&A, please? So let me just start with a quick question. You said it's the sort of computational effort was about the same as sort of a hybrid functional, something like that. Does that mean that your sort of method on top of that is incredibly quick?
Yeah, it depends, of course, of what value of eta you choose then, right? So if you choose eta very low, then basically you get the cost of a canonical couple cluster solution, which is too expensive. The question is, what accuracy do we need, basically? And so it's a bit difficult to make good statements about the scaling. But basically what we say is that for a fixed value of eta, the scaling should be just a third order for the correlated part for a fixed value of eta. And the other statement that we think is true is that as you scale up your system size, the value of eta that you need for a given accuracy per electron, you don't need to go lower in eta. We think that's true, but it's and we did some testing on that, and it seems to be true. But there's, of course, some kind of long-range effects, dipole-dipole interactions, and so on that you really need to also take care of, that they're properly included.